Hello and welcome to C++ Weekly. This is a special video about C++ allocators that was produced in cooperation with Bloomberg. The views and topics presented in this video are entirely my own. So this video is a continuation on the PMR video that I did, it's been a few months ago at this point. And when I ended that video, I left you with something that was kind of like this. I made the claim of 3.5 times faster standard containers using PMR in C++17. And we had some nice chart that looked something like this. Now this particular one is 2.5 times faster, but I'm using standard list with PMR and a monotonic buffer resource versus standard list without that. And if you recall, a standard list has to do an allocation for each element in the list. And that's a lot of memory being allocated and a lot of memory indirections. And a monotonic buffer resource with PMR gave us a way of putting this all into one flat memory space. And it was a considerable savings because all of this lived on the stack, not on the heap. So you're probably left with a lot of questions when you saw that video about what are the real use cases for this? What might the limitations be? What is the practical real world implications? And potentially what the heck is PMR anyhow? I didn't even really go into that. So let's start at the beginning and say, what exactly is PMR? So all the PMR list is a type def or a using declaration to say use this standard list with this polymorphic allocator. And the point is to give us a type erased way of working with memory resources and allocators so that it is easier to combine and layer these things in different ways and have containers that contain things that are themselves allocator aware without having to write quite as much boilerplate code. So the standard allocator, which is the default type def here, if we're not in the PMR, is just one that uses new and delete resources. So you're always using an allocator of some sort. It's going to be one that uses new and delete, or it's going to be one that uses your own rules and your own buffer. And a memory resource here is the virtual interface that is used for allocating and deallocating memory so that it can be inherited by your own custom allocators or the ones that are in the standard library. So for our use case in that last example, we showed the monotonic buffer resource, and it gave us this incredible performance results from our standard list example. And all this is this monotonic buffer resource. It inherits from this PMR memory resource with the virtual interface that we said. So yeah, it does have to do a virtual function call, but if you consider that it's only doing a virtual function call during allocation and deallocation, then those are things that you're likely avoiding anyhow, but they are considerably cheaper than calling the global new and delete, if you can come up with a memory allocation strategy that works well for your code. So we need to understand what the monotonic buffer resource is. So this is a special purpose memory resource that releases allocated memory only when the resource is destroyed. So if I call the do deallocate, this is a no-op. This is important to remember if you're using the monotonic buffer resource. It is intended specifically for very fast memory allocations in situations where memory is used to build up a few objects and then is released all at once. So in the case where you're growing your objects and you're growing your containers over time, this is probably not the best option for you. And I'm going to demonstrate exactly what that means. So in this episode, we're really going to dig into what it looks like to allocate memory and what it looks like to use this monotonic buffer resource and what use cases it may or may not be good for. But before we continue here, there is one very important topic that I need to bring up that might greatly affect whether or not you can use PMR on your project. So let's look at our polymorphic memory resources support from cppreference.com here. And we can see polymorphic memory resources are supported as of GCC 9 and Visual Studio 19.13. So let's just hover over that. That's Visual Studio 2017 or version 15.6. So it looks like one of the later releases of Visual Studio 2017, which is fine. We're on Visual Studio 2019 right now. Now, what you may notice are these blank red boxes here. We have no support in lib C++. Clan's standard library implementation does not support polymorphic memory resources. So if you're using it, you can't use PMR with your build chain, but you can with lib std C++. That is the GCC implementation. So it is entirely possible that by the time you're viewing this video, support for polymorphic memory resources will in fact be in Clan's standard library. What I have written here are a couple of helper functions, print buffer, which calls print line, and these two functions together basically dump out all of the stuff that's in the container that we are manipulating and is inside of the buffer that is backing this container. And it prints 16 bytes at a time and gives us a way to look at the data that's in here. And I've already got one output here, but I'm going to demonstrate what this is, and we'll rearrange these window sizes in a moment. So I've got a bunch of potential things here that will be coming over the next couple of episodes, but at the moment I'm just going to demonstrate this, quote, growing resources. Now, if you recall, this says it is intended for very fast memory allocations in situations where memory is used to build up a few objects and then is released all at once. It's not a general purpose allocator. So I have growing resources here, and this example, I am creating my buffer of 16 8-bit bytes, 16 elements that are 8 bits. And then I create my monotonic buffer resource that is backed by this 16-byte buffer. And then I create a vector that is using this memory resource. I push back one element, and then I am dumping this information here with this heading 1. Then I push back a second element, a third, a fourth, and a fifth element. So let's actually see what this looks like. So our very first element that we push back, this is the value 1. You can see that here where my pen is hovering, and we can see this element 1. We can see that this buffer starts at this location of memory. Now, if you're used to looking at memory addresses in your debugger, it should be a telltale sign here. This high memory address is going on the stack. And I am adding one element to it here, and we can see that the first element has the memory location that is shared with the 0th element, and the memory address of our buffer are exactly the same. So no problem, exactly as expected. Now over here, I am pushing back the second element and printing it out. Now what we notice is we see a 1. That is this. But when a vector is allocated, it only allocates enough room for not exactly as it needs, as much as it needs to. It grows, right? So it grows by a certain capacity each time. So that's fine. But then when we grow it and add the second element, what we end up getting is this element copied in, and then the 2 being added to it. I'm going to stick with my red pen. It's a little bit more viewable. So this element here, and then we get this. So this is one allocation now. And we can see that the first item starts 1 byte after buffer address. So I push back here my third element, and we dump that. And we see this allocation for the first element, this allocation for 1 and 2, and then this allocation for 1, 2, and 3. And each time the first element is being moved where it starts. And so clearly this is not the best use case for a memory resource that never actually frees memory. What we can see here when we go to the fourth element that it has not done this extra. So we've got those two, than those 4, because the vector reserved a capacity for 4 elements. It's going to grow geometrically like this. It doubles each time. So then when we add a 5th element, it does in fact change this start position of the data that's in here again, okay? So what we're seeing is, like I said, we're seeing that the memory is never actually freed. And if we scroll down one more time, then we see something like this. So if you're growing memory, not a good use case for the monatomic buffer resource. You need to understand what the limitations are so that you can take good advantage of it. So we need then to, try to get a handle on what actually are good use cases for it. I have this example here that I've called the nested string, and this is a vector, again, of strings now in this case, that is backed by this monotonic buffer resource. I've made this particular buffer backing much larger. It's not the 16 bytes in the last example, it's 128 bytes here. And I'm printing out the size of string here so we get a little bit more information. Let's add a new line here. Now, we already know that growing this memory is generally not a good idea. Because each one of these in place backs is going to have to reallocate memory for the vector, and this doesn't get freed by the monotonic buffer resource. We can still use this as an illustration to show what is happening underneath, or we can just go ahead and merge these two things together. So let's just go ahead and initialize this, because this is a much better use case. So I've got my 2 short strings that I am initializing into this vector, and we'll discuss what that means in just a moment. And then we'll build on this. And all these examples will be in the links so that you can look at them on your own in the video notes. Okay, so we have our 2 short strings output here. And there's a couple of things that we need to notice. Something that we didn't comment on before is we've got this very first element here. This is my hello world string, and it starts here. Now there is definitely something missing. And the thing that is missing is the information about the vector itself. Now keep in mind, the vector doesn't live in this buffer. Only the data that the vector contains lives inside this buffer. So on the stack, we've got some buffer that's 128 bytes long, and it has all this data in it. That is where we created this. And then underneath it, in the stack, we've got the actual vector. And the vector now has a couple of pointers and some length, something like that, that points actually into this memory location here. So that's why we're able to see all of this data just laid out here without any kind of header in front of it. So we can, if we look at this, since I did this on 16-byte alignments here, we can actually see the data that represents the information about the string. So we've got the string that starts here, hello, and then a space, world, and then a 0, the null terminator for the string. And we have here 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We've got 2 8-byte things here, which should correspond to the start of the memory. So that's 7F, FD, FD, 83, 83, F6, F6, F0, F0, 90. So this data starts 10 off, 10 hex off from the beginning of our allocator, and it's right there. Okay, so that's the hello world string, exactly where we expect it to be. And then we also have hello world 2 down here. Now, there's something special about these two, and that is namely the fact that all standard libraries implement something called SSO. This is the small string optimization or short string optimization. So if your string is, let's see, this is got an extra space here. We can see the length is 13 on this one and 11 on this one. If your string is longer than what can fit inside this buffer, so we have the length of a string on this particular platform, or the size of a string is 32. 32, so that is 16, 32. It just takes up these two rows. So if your string can fit inside this 16-byte buffer that's built into the string object, then good for you. If it can't, it has to go somewhere else. Well, where is somewhere else? Let's make a third string that should easily fit in here because we've got 128 bytes available to us and we're currently only using 64 of them. And we're just going to call that hello world long string and let that compile and we'll get a dump of it. Okay, so it is printed out now. Let's go ahead and come down here. And we need to look at this data again. We know that this is the start address of the string. And this is its length, 11. And then we've got the start address here. And its length is OD or 13, depending on whether we're looking at the hex, the decimal, or the ASCII representation here. And then that's hello world 2. That means we know that is string 1, that is string 1 and string 2. We know that this represents the third string. So this first bit, if everything is the same, that is our length, that is 23. And this memory address now looks quite a bit different here. We're no longer starting at 7F, here we're at a different memory address. And so what it is a pointer to the heap where this value needs to go. So it kind of comes across like, you know, if we've got, this is in our allocator, and this one's in our allocator, but this one is now on the heap. That kind of defeats the purpose of using a custom allocator altogether, which brings us to our next point, and that is how to have allocator-aware objects inside of other allocator-aware objects. I have here a vector of strings. Well, standard string is a container just like any other container in the C++ standard library. So we can use actually standard PMR string. And now we will get something that has the same allocator type, PMR allocator, as the vector, and therefore the vector will automatically propagate its allocator down into the string. And when we do this, we'll be able to actually see all of this data right here in our monotonic buffer resource, presuming that we have enough space. We're currently using 6496 bytes, that is for the 3 string objects, and we don't yet have anywhere to actually put this long string. So let's go ahead and make this a little bit bigger. So the title of this is becoming increasingly wrong. This is 2 short strings plus 1 long string, but that's okay. We can still see the data coming in here. We've got new information. We've got now some, our string objects have gotten longer. They've gotten bigger because they're these PMR strings now. They have to keep a pointer to their allocator or a copy of the allocator. So we can see the hello world come in there. And then we can see the hello world 2. And we can see the hello world long string. So it is definitely worth mentioning what happened in the first place. I had to, or if I didn't expand the size to 120, 256 bytes, and I was only at 128 bytes, and it didn't have enough storage here, the monotonic buffer resource is smart enough to automatically go to the heap if you go beyond the size that it was given. So that's good. It prevents, a memory error or a crash or whatever, and we still end up with one giant chunk of contiguous memory allocated that does what we want it to. It's just not on the stack anymore. And keep in mind, when it goes to the heap, it still has this, it doesn't free when things grow. So you have the possibility of limitless memory growth when you're using the monotonic buffer resource, but there are other allocators and you can write your own allocators. And for one quick other note, let's just go ahead and see what the impact was here of moving to PMR string. So this debug output that we're playing with, where we're dumping all of these values, actually has the correct information in it now. Okay, so our PMR string size, this is important to note, is now 40 bytes. It is not 32 bytes. So that first 8 bytes is going to be a reference to the actual underlying memory resource and it allocator, and it plausibly can change depending on the type of allocator, but this is with the PMR one. It adds 8 bytes. That's not that bad. So our key takeaways here are so know how and if your memory is growing, choose the correct allocator for your use case, and make sure you properly nest your allocator-aware types. In the next episode, we're going to talk more about building your own allocator-aware types and what that actually means and how you can do this on your own, because right now if you just create a struct and throw it into a vector, it's not necessarily going to do what you want it to do. And you also need to understand which of the standard types are allocator aware and can work with your custom allocation strategy. And we'll again talk about more in that in the next episode. So I hope you enjoyed this special episode with more of a deeper dive into taking advantage of allocators in C++ 17 with PMR. Be sure to subscribe, and thanks for watching.